Hello everyone, welcome back. In this video I'm going to show you an example of a ladder circuit, a circuit essentially that includes something that looks like a ladder that is made up of resistances. So here's the topology that we're going to study. We have a 9-volt power supply right here. It's an ideal voltage power supply. And then we have several resistances connected in what people would probably recognize as a ladder network. It's the topology you see right here, and you could have a very small or a very long ladder. I have chosen kind of a medium size, if you will, here. And we're being asked to find the current I that this network will draw from this source right here, and the voltage V. And the voltage V could really be anywhere in the ladder. I have chosen it here to be the voltage across the 12-ohm resistance. Now, probably the best approach that most people will be thinking about here is to simplify this network. Somebody will say, how can I start combining things here to make things look a bit simpler? So perhaps I can apply voltage division, Ohm's law maybe, something to help me find what I need. So one of the difficulties here is that some people will start combining, for example, this 5-ohm resistance with this 3-ohm resistance and say, well, these guys seem to be in series, so why can't I just combine them? And if I do, how do I really redraw my network here? Well, the reality is that these 5-ohm and 3-ohm resistances are not in series because they don't have the same current. So any current that will flow through the 5-ohm resistor could decide to continue to the right, or it might actually go downwards. So for sure, they are not guaranteed to have the same current, and therefore they're not in series. All right, somebody else says, fine, I see why this idea doesn't work. What about this 12-ohm resistor with this 6-ohm resistor? Can I actually combine these in parallel? After all, they're drawn to be exactly parallel to each other. Is it not true that they're connected in parallel? Well, again, let's apply what we have studied. We have studied that two resistances are considered to be connected in parallel if they have the same voltage drop. And that would require that their bottom nodes are connected together, and indeed the bottom nodes here are connected together, and their upper nodes are also connected together. Well, here we have an issue, because this node is connected here, and the other resistance node is connected there. Well, you might say they are connected together. The answer is no, they're not. Look at this 3-ohm resistance. That 3-ohm resistance will have some amount of current through it, which will make sure that there is some voltage drop here. And this voltage drop, in general, will be non-zero. And therefore, this green node will be at some voltage V1. And this blue node will be at some voltage V2, which practically means that they will not be the same. And therefore, these two resistances, even though they're drawn in this ladder as nice parallel resistances, they are not connected in parallel, and therefore I cannot simplify them in any reasonable way. So as you can see, it's not as simple to start combining things here, at least by taking a superficial look at the circuit. So the trick to simplify the circuit is to always start from the end of the ladder. Always start from the point which is farthest possible from the source. That's what I mean, end of the ladder. Start from the very end, from the last resistance, and then move your way towards the source. If I do that in this case, I will immediately come up to this 2-ohm resistor, and this 2-ohm resistor is indeed now connected in series with a 4-ohm. Why is that? Because any current through the 4 ohms now must go through the 2-ohm resistor. There is no other path. The ladder has ended. There is no other path that the current can follow. So 4 ohms and 2 ohms are indeed connected in series. I can go ahead and replace them with one resistance whose value will be equal to 4 plus 2, or simply 6 ohms. I achieved my very first step. If you thought of that, that's great. You should be proud and continue. Now this 6-ohm resistance now is between this blue node here and this blue node there. That's wonderful because I have another 6-ohm resistor that is also exactly between the same nodes. These red nodes that I put are exactly the same as the blue nodes. Once again, these two are connected with a source, so they're exactly the same nodes. So I can go ahead and combine the two resistances that exist between these common nodes with just 1. So I'm going to replace this thing with just one resistor that is connected between these nodes, and the value of that resistor will be 6 in parallel with the 6 ohm that I just calculated, or that should be equal to 3 ohms. So now between these two nodes I have a 3 ohm resistance, and this 3 ohm resistance is now in series with this 3 ohm resistance. Why? Because this entire 3 ohm resistance that imagine now has existed here, it replaced everything else I had before, will have exactly the same current as the 3 ohm resistance that was given to me in the circuit. That means that this 3 ohm is in series with this 3 ohm, resulting in, of course, 3 plus 3 equals 6 ohms. So let me actually simplify a little bit the circuit and redraw it down here so you can see it. So in this last step, I have the 9 volts, which is exactly what I had in the very beginning. I have this 5 ohms, which is what I had in the beginning. I have this 12 ohms, which is what I had in the beginning. And now that 3 ohms with this this big box of 3 ohms have been combined to give me 6 ohms. So this is now how the circuit looks like, and the original voltage drop V exists now here. And the original current exists now here. Nothing really has changed from that point of view. So now I have to keep going. I have to keep simplifying the circuit. My next natural step now is to combine these two resistances. Hopefully you can see that these two resistances are connected now in parallel. So I have this common node for both of them, this common node for both of them. So that means that 12 ohms connected in parallel with 6 ohms will basically be, based on the formula we've learned, 12 times 6 over 12 plus 6, or 4 ohms. So now I have done one more simplification, and let's move on to the next slide so I can give you the simplified circuit, which I just did. And here is my final circuit. Now, somebody might say, wait, there is one more simplification you could do. Why can't you just replace that by combining these 5 ohms with these 4 ohms? Aren't these not in series? The answer is yes, of course they are in series, but why would you want to combine them? In fact, if you did combine them, you would actually lose this voltage drop that is one of the unknowns in the circuit. So you should remember we're combining things in a way to simplify our circuit. We're not just blindly combining or making every possible equivalency we can see in the circuit, because this actually might hurt us. It will particularly hurt us if we lose a voltage or a current that we want to find, or if we lose something that we need as a controlling variable, perhaps for a dependent source. So you should be very careful. Combining in general is good. It does lead to simplified circuits, but think about before you combine, am I losing something I want to find, or am I losing something that controls another source in my circuit? If the answer is yes to either of these two questions, you should hold on and think of a different approach. In this case, I have actually simplified my circuit enough that I can go ahead and find what I need. For example, the current I here that I want to find is very simple. It's the amount of voltage that I have, which is 9 volts, divided by the total resistance that I have between this node and this node. And the total resistance is nothing else but 5 plus 4. Why? Because these two resistances, as we just discussed, are connected in series. So this current I that I need is nothing else but 1 amp. Now, similarly, this voltage V that I need can also be found very quickly from that circuit. One thing I can do is I can apply Ohm's law because I know the current. So this current I will simply continue flowing in this loop. I have passive sign convention, so I can write down that V is equal to IR, and this will be equal to 1 amps times 4 ohms, or basically 4 volts. If you don't want to apply Ohm's law, there is another way to solve the circuit. You can go ahead and simply apply voltage division. So that same voltage V can be calculated by saying that this is equal to 9, the total voltage drop I have across both resistors, times the resistance I want, which is 4, over the total resistance, which is 5 plus 4, or of course this is equal still to 4 volts. And that basically completes the calculation. I got my 1 amp current, I got my 4 volts, and the circuit, as far as we're concerned, is actually solved. So let me try to summarize a couple of key things you should keep in mind. In this video, you actually learned what is a ladder, and you learned a couple of useful approaches of how you approach simplifying a ladder. You simplify a ladder by starting from the very end, the point that is the farthest possible from the circuit, from the exciting source rather, and then move your way towards the exciting source. And simplify only as much as you need. Simplify only up to the point that you can solve the circuit and you don't lose any controlling variables or any of the unknowns that you have. So thank you for watching this video. We will see you next time.